Imagine drifting silently over our planet, more than 250 miles above its surface, aboard the International Space Station. Below you, the world is shrouded in night, with only the faint glimmer of city lights and the occasional flash of a thunderstorm breaking the darkness. Suddenly, a burst of electric crimson and cobalt blue erupts high above the clouds. A fleeting, ethereal flash that ripples through the upper atmosphere and then vanishes as quickly as it appeared. This is no ordinary lightning. It is a sprite, one of the most enigmatic and spectacular phenomena in the natural world. Recently, astronaut Nicole Vapor-Ayers witnessed and photographed this marvel, offering humanity a rare glimpse of a phenomenon that, for centuries, lived in legend and mystery. But sprites are only one member of a hidden family of cosmic wonders known as Transient Luminous Events, TLEs for short. But what truly are sprites, and why have they captivated scientists, engineers, and skywatchers around the globe? Could understanding these luminous bursts high above the clouds unlock secrets vital to our technology, climate, and very existence? Sprites are awe-inspiring, large-scale electrical discharges that happen not within thunderclouds, but far above them, generally between 30 and 60 miles up, in a layer of the atmosphere called the mesosphere. Picture a fireworks show orchestrated by nature, tendrils of red, blue, and sometimes purple light, branching and dancing in intricate forms that resemble carrots, jellyfish, or even angelic figures. Some sprites can stretch vertically for dozens of miles, dwarfing the largest bolts of lightning that occur closer to the ground. Their ghostly beauty has inspired countless stories, but their reality was only confirmed in the late 1980s. Long before science caught up, humanity had already noticed strange lights above thunderstorms. Pilots in World War II reported seeing mysterious glows flickering above distant clouds. Ancient chroniclers wrote of fiery messengers leaping between heaven and earth. Indigenous cultures wove tales of spirits or gods casting lightning above the world. Yet, for centuries, these reports were dismissed as superstitions or tricks of the mind. It was not until the summer of 1989 that a team at the University of Minnesota, testing sensitive low-light cameras, accidentally captured two distinct flashes of red above a thunderstorm, recording the first scientific evidence of sprites and opening the door to a new area of atmospheric science. Sprites are only one variety in the broader category of transient luminous events. This family includes elves, expanding rings of light triggered by electromagnetic pulses, blue jets which shoot upward from the tops of storms into the stratosphere, halos, disc-shaped glows that often precede sprites by mere milliseconds, and gigantic jets, spectacular discharges that can soar up to 60 miles, bridging the gap between thunderclouds and the very edge of space. Each of these events offers insight into the electric heart of our planet and the forces that shape our weather and climate. But what causes sprites to burst into existence? The answer lies in the extraordinary energy of thunderstorms. Most lightning that strikes the ground is negative cloud-to-ground lightning, but sprites are triggered by a much rarer form, positive cloud-to-ground lightning. These positive bolts, though less common, carry several times the current of their negative counterparts, sometimes reaching hundreds of thousands of amperes. When a positive bolt strikes the ground, it creates an immense imbalance in the electric field above the storm. This imbalance is so powerful that it causes the thin, cold air in the mesosphere to break down, exciting nitrogen molecules and causing them to glow with radiant reds and blues. Hans Stenbayek Nielsen, a leading researcher at the University of Alaska Fairbanks, explains, "Sprites are a manifestation of a fundamental electrical discharge process in the atmosphere. Unlike traditional lightning, sprites are nearly silent. Their energy radiates upward and outward, sometimes spanning hundreds of miles across the sky, but they do not produce the familiar thunderclap we associate with other electrical discharges." The science of sprites is still young, but it is advancing at a remarkable pace. Agencies such as NASA and the European Space Agency have devoted substantial resources to studying TLEs. Ground-based optical and radio sensors, high-altitude aircraft equipped with sensitive cameras, and orbital platforms like the International Space Station have all become part of a vast observational network. The ISS, circling Earth every 90 minutes, has emerged as a frontline observatory. Astronauts with digital cameras have captured hundreds of breathtaking TLE images. The European Space Agency's Atmosphere-Space Interactions Monitor, ASIM, was specially designed to observe these elusive flashes and is collecting data never before available from the ground. But professional scientists are not alone in this quest. Citizen science is now at the heart of TLE research. NASA's Spectacular project invites anyone with a camera or smartphone to hunt for sprites and related events. Hundreds of skywatchers, from amateur astronomers on the Great Plains of North America to intrepid photographers in the Himalayas, have contributed their images and observations. According to Burcu Kosar of NASA's Goddard Space Flight Center, Spectacular will bridge the gap by creating the first crowdsourced database of sprites and other TLEs. This collaborative effort is enabling scientists to map these rare events on a global scale, revealing patterns that were invisible only a decade ago. Despite rapid progress, profound questions remain. What is the full nature of TLEs? How do they form? How often do they occur? And what impact do they have on the upper atmosphere and human technology? Scientists like Yoav Yair from the Open University of Israel emphasize that this research is not mere curiosity. It is essential to our safety and technological well-being. Sprites are not just beautiful spectacles. They represent massive transfers of electrical energy between the ground and the edge of space. Could this energy disrupt satellites, interfere with radio communications, or even threaten aircraft? To answer these questions, we must look at the global electric circuit, a planetary system in which thunderstorms act as generators, moving positive charge to the ionosphere and negative charge to the Earth's surface. TLEs, especially sprites, are believed to return some of this charge from the upper atmosphere back to Earth, maintaining the planet's electrical balance. When a sprite occurs, its surge of current can induce very low-frequency radio waves, VLF perturbations, that ripple through the ionosphere. These waves sometimes disrupt the signals that power global navigation systems, aircraft communications, and even the power grids that keep our cities running. Engineers are now carefully studying whether such sprite-induced VLF events could cause data blackouts, navigational errors, or degrade satellite electronics over time, potentially affecting everything from intercontinental flights to emergency response systems. The aviation sector is watching closely. Modern jets routinely fly at altitudes where the effects of TLEs may be felt. While direct encounters with sprites or gigantic jets are exceedingly rare, the energetic electromagnetic fields generated by these events could, in theory, interfere with onboard electronics or communication systems. Some researchers are exploring whether repeated exposure to sprite activity might slowly erode protective coatings and materials on aircraft, increasing long-term maintenance costs and raising new questions for airline safety protocols. Then there is the question of climate change. As global temperatures rise, both the intensity and frequency of thunderstorms are expected to increase. Studies already indicate that the number of sprite-producing storms is on the rise, especially over regions like the Great Plains of North America, the Amazon Basin, Central Africa, and the foothills of the Himalayas. Martin Fullekrug of the University of Bath notes, "Understanding the link between lightning and TLEs is essential for improving space weather forecasting. If climate change is producing more powerful storms, and by extension more sprites and other TLEs, are we heading toward a future where disruptions to technology, aviation, and even the global electric circuit become more frequent?" The chemistry of the upper atmosphere is also at stake. Sprites and TLEs can trigger reactions that produce nitrogen oxides and other compounds, subtly influencing the composition of the ozone layer. While each event is fleeting, lasting only a few milliseconds, the cumulative effect of increased TLE activity may alter the delicate balance of gases that shields life on Earth from harmful ultraviolet radiation. Dr. Yoav Yair cautions, "We are only starting to grasp how changes in climate might trigger more sprites, and what that means for both the skies and the systems we rely on." To further illustrate the scope of this phenomenon, imagine the global tapestry of thunderstorms. At any given moment, thousands of storms are active worldwide, generating millions of lightning flashes each day. Among these, only a small fraction, perhaps 1 in 100, are positive cloud-to-ground strikes, the type that can spawn sprites. Yet, even this tiny proportion adds up to tens of thousands of sprite events every year. The strongest sprite-producing storms tend to cluster over specific regions: the Great Plains of North America, where vast thunderheads rise to dizzying heights; the Amazon, where convective storms churn almost year-round; the mountainous regions of Central Africa; and the high-altitude valleys of Asia, where Gaopeng Liu of the University of Science and Technology of China has observed some of the most complex and intense upper atmospheric discharges ever recorded. The diversity of TLEs is remarkable. Besides sprites, which often appear as red, carrot-shaped forms with hanging tendrils, There are elves, vast, donut-shaped rings of light that can expand outward at the speed of light, sometimes covering areas over 200 miles across. Blue jets, shooting upward from thundercloud tops, can reach nearly 30 miles into the stratosphere and are sometimes visible to pilots. Gigantic jets, the heavyweights of the TLE family, have been documented climbing all the way from the cloud tops to the lower reaches of the ionosphere, forming spectacular bridges between Earth and space. Sprite halos, faint disc-shaped glows, often precede sprites by a few milliseconds, serving as a kind of prelude to the main event. Spectral analysis of sprites reveals that their radiance is dominated by red emissions, primarily due to excited nitrogen molecules. Occasionally, tendrils of blue or violet can be seen, especially in the lower parts of the sprite, where the atmosphere is denser. The altitude at which sprites form is influenced by the density of the neutral atmosphere. The thinner the air, the higher the sprite can develop. Scientists continue to refine their understanding of these details, using high-speed cameras, radio receivers, and even satellites equipped with photometers and spectrometers. Looking to the future, the possibilities are both thrilling and daunting. Imagine a planet-wide network of sensors, ground stations, drones, high-altitude balloons, and satellites, all working together to monitor every sprite, jet, and halo in real time. Such a system could revolutionize weather forecasting, providing early warnings for storms that may produce disruptive TLEs. Meteorologists could alert airlines to reroute flights, communication companies could adjust satellite operations, and emergency services could prepare for power grid disturbances linked to atmospheric electricity. As artificial intelligence and machine learning continue to advance, these networks could one day predict TLE outbreaks hours in advance, fundamentally changing how we manage and protect technological infrastructure. But the implications stretch even further. The study of sprites and TLEs is opening new windows into the fundamental processes that shape our planet's atmosphere. Stephen Kummer of Duke University observes, "Studying TLEs helps us understand the coupling between the lower and upper atmosphere. This coupling is crucial, not just for weather forecasting, but for understanding the broader climate system and predicting how it may evolve in the coming decades." There are also tantalizing prospects for technological innovation. By unraveling the secrets of atmospheric electricity, engineers may one day harness its energy, developing new methods for lightning protection or even atmospheric energy harvesting. Picture cities shielded by intelligent systems that can detect and divert dangerous electrical discharges before they strike, or power networks that dynamically respond to the ebb and flow of the global electric circuit, reducing outages and improving resilience. Beyond technology and science, sprites carry a certain poetic mystery. For most of human history, their existence was denied or ignored. Even as recently as 40 years ago, many experts refused to believe they were real, despite persistent reports from pilots and explorers. It took the lucky capture of a single photograph and decades of determined investigation to bring sprites into the scientific mainstream. Today, they are at the forefront of space weather science, inspiring a new generation of explorers and researchers. So what does this mean for you, sitting at home under the same sky? First, it is a call to curiosity. The next time a summer storm rumbles overhead, do not just watch the lightning. Look higher, far above the clouds, and you might glimpse the silent ballet of sprites. If you have a camera, or even a smartphone, you can join the worldwide network of citizen scientists, contributing valuable data that helps rewrite the textbooks of atmospheric science. NASA's Spectacular project welcomes your participation, and your observations could help solve one of the greatest mysteries in modern science. Second, it is a reminder of the profound connections that bind us to our planet and each other. Every sprite, every jet, every luminous flash is part of a vast circuit linking the Earth, the sky, and the edge of space. These events ripple through the electric web that powers your phone, guides your airplane, and keeps your city's lights glowing. As our world becomes ever more reliant on complex technology, understanding and safeguarding this electric environment is more important than ever. And here is a secret. For generations, sprites were relegated to myth and rumor. Only in the last 4 decades have they moved from the realm of legend to the laboratories of science. Now, thanks to the efforts of astronauts, scientists, and citizen observers, sprites are helping us understand not just the wonders of the upper atmosphere, but the deep electrical ties that bind our planet together. In the end, our quest to understand sprites is about more than solving a puzzle. It is about preparing for a future shaped by forces both seen and unseen. It is about protecting the technologies we depend on and embracing the wonder and complexity of our ever-changing sky. If this story has ignited your curiosity, subscribe for more deep dives into the hidden forces shaping our world. And the next time a thunderstorm passes overhead, take a moment to wonder, what secrets might be leaping above the